our airplanes for a population. The first thing we're going to start with today is a sample standard deviation. The one thing you're going to notice is on your purple packet, all these formulas are on there. The formulas look very similar, whether it's population versus sample, and they're labeled under Chapter 2 which one's which. If it is a sample, instead of the little lowercase sigma, it looks like a circle with a line over it, we're going to see a lowercase s instead. Variance is still the one that is squared. Standard deviation is not squared. So if you have variance, all you do is take the square root to get the standard deviation. The formulas, if you compare this to the population one from yesterday, you're going to see instead of mu, which kind of looks like a U with the extra little line on it, we have x bar. That represents the mean if it's a sample. And in the denominator, the difference is instead of n, and it was a capital N for population, it's now an n minus 1. So we take 1 away from our sample size. That actually has us, allows us to get a bigger number for the standard deviation, and that allows us to have a little bit more room for error because we're only calculating based off of the sample, which is a small portion potentially of the larger population. So the bigger room for error when we do that calculation. Okay, so calculations as far as like the tables and everything go are going to be similar. You just got to get used to kind of the different variables you're going to see based on whether your data set is a population data set or a sample data set. This little slide will be in Polaris for you. It's just kind of like a little side-by-side comparison of the variables that you're going to see in population formulas versus the variables that you're going to see in the sample formulas and the difference between the two, okay? Still represent the same thing, but we're going to see some different Greek letters and whatnot popping up as we do this. All right, so what I want you guys to try to do on the back of your handout from yesterday is another example where we can practice calculating the standard deviation. So here, this represents a group of high school football players that suffered concussions, and these represent the number of days it took them to recover from the concussions. So you're going to use these values, and you're going to use the updated formulas for sample, which again on your purple packet, to calculate the standard deviation. So the setup's going to be similar to what we did yesterday with the planes. These are what you can title your columns. Okay, so the recovery times are going to be your first column, and that's your x. The second column is still going to be our deviation that we practiced yesterday. It's x minus the mean, but now the mean is an x bar. So you do need to calculate the mean in order to fill out that column. Remember, those could be positive or negative. The third column is your deviation squared, which in symbols for a sample is going to look like this. Okay, so all the calculations you can use yesterday's example to help you through it. It'll look pretty much the same, except at the end you're going to divide by instead of 10 and minus 1. Okay, so go ahead, you can work together if you want. I'll give you a few minutes. We'll put the answers up, we'll check them. I'll also show you how we can check it in the calculator when we're done too. Okay, all right, go ahead and get started. You can fill a little more in if you need to here. There we go. Okay, so first column is your recovery times. You have to calculate the mean, so add them all up, divide by 12, you get 7.5. And then you're going to take each x value minus the mean. So that first column, if you want to check it as you're going, remember it should always add to 0, and this one will be exactly 0 because we didn't have to round the mean at all. Then we take the second column and square them all, and that gives us the third column. So because we're squaring, that third column should always be positive. And the sum of that third column is that ultimate number that we're looking for. So 39 is the number that we did all this work to get. Then your variance formula for a sample looks like this guy. The numerator, this whole thing, is what we just calculated. So these are, remember, like our set of instructions. We did all the deviations, we did all the deviations squared, and then we added them all up. So we got 39 on top. The denominator, our n in this problem, is 12. If it's a sample, we just have to remember to take away 1, divide by 11, and we get our variance. And then once you have variance, really we're just taking the square root of that number to get our standard deviation, which is about 1.8. Okay. After you're done correcting anything, I want you to put this data in your calculator in list 1, like we practiced. So you just hit Stat Edit, remember? Any questions on what's on the board? Okay, there. Okay, so once you got your data in the calculator, again, stat edit is how we get it in there. You can clear out the list. Then we're going to do that one variable statistics calculation like we did before. So we're going to hit stat. We're going to go to the right where it says calculate, and then we're going to hit enter over one variable statistics, option number 1. Hit enter a few more times, and it spits out that big list of things that we were looking at before with like the mean and the median. Now my picture here is not that particular data set, so you're going to see different numbers, but on yours you should see similar numbers to what we just calculated for a couple of things. So whether it's a population or a sample, X bar is where you're going to look for the mean. So if you just put our data in there, X bar should be 7.5 in your calculator right now. It should also give you an N of 12 if you look at that value, total number of data values we had. Okay, then I want to draw your attention here. So the calculator is always going to give you 2 standard deviations, and you have to know which one to look at for your particular data set. The one with the S is for sample, and the one with the lowercase sigma is for a population. Your calculator doesn't know if the data that you're putting in there represents a population or a sample, and the formulas are different. One we divide by n, the other we divide by n minus 1. So it accounts for both, and then you just have to know, oh, I'm calculating it for a sample. I look at the one that says S. So in this case, that's the one you guys should be looking at. What we just calculated, it was 1.883, so you can check that number. And then if it was a population, you're going to see the standard deviation just a little bit smaller because we don't have to leave that extra room for error. Okay? Any questions on just checking it? Definitely a good option for Math Excel questions, especially if you've done 1 or 2 by hand, or if you just want to type it in before you use up one of your attempts. All right, so the new thing that we're going to start talking about today is the spread of data. You don't need to write this down. I think this is just a nice picture to see when we talk about what the standard deviation actually represents. So the smaller the standard deviation, the closer to 0, the closer your data is to the mean. And the bigger your standard deviation, the more spread out it is from your mean. So if we look at these 3 pictures, all 3 of these have a mean of 5. But we have a standard deviation of 0 for this first one because all of the data values are at 5. They do not differ from the mean at all. Then as my S value gets larger, you can see the data values start to get further and further apart from the mean. I don't expect that you look at this and say, oh yeah, I know the standard deviation is going to be 1.2. It's something that's a little harder to calculate. But the idea that the standard deviation is just getting bigger and bigger as the data is more spread is kind of what you want to get from these pictures. Okay, that's what we're looking at. That's what that number is telling us. The most common way that we see a distribution of data is with what we call a bell-shaped curve or a normal distribution. You're going to hear those words a lot, normal distribution, bell curve. This is called the empirical rule. The empirical rule is on your purple sheet. At the very bottom, I think, of the left column on the front there, it says 68, 95, 99.7. You guys see it? Okay. So it tells us if we have this normal shaped curve, number 1, it's symmetric, so my mean is right in the middle. Then what we see here are 1, 2, and 3 standard deviations to the right, 1, 2, and 3 standard deviations to the left. The empirical rule tells me approximately what % of the data is within 1, 2, or 3 standard deviations. So if I am 1 standard deviation to the right or to the left of my mean, total, I've got about 68% of my data condensed there. It's this shape. If I'm within 2 standard deviations, it's 95. And if I'm within 3 standard deviations, that accounts for almost everybody, 99.7% of the data. It's a little bit extra in these little tails that we say, but most of it's within 3 standard deviations. When you see a shape like this, it's kind of like, you guys remember talking about asymptotes in like previous math classes where we get really close to a line, but we don't touch it? That's what's happening here. This curve is never going to intersect that horizontal axis. It just kind of hovers above and gets really, really close on the end. So sometimes you'll see pictures where it almost looks like it's touching just because it's so close, but it doesn't. What I want you guys to do on your purple packet, just on the front page there, I want you to draw this picture, and I want you to include these numbers. Okay, so if 68% of the data is within 1 standard deviation, I can take that 68 and I can divide it in half and say 1 standard deviation to the left or 1 standard deviation to the right is 34% of my data on each side. Then, if I take the 95 and the 68 and I find the difference between the two, I get 27. Divide that in half, there's about 13.5% of the data in the next standard deviation out. And then the last one is 2.35. Okay, so again, 34, I'll make those numbers a little bigger, 13.5 and 2.35. If you add all of those up, they do not add up to 100%. They add up to 99.7 because that's just within 3 standard deviations. So there is also, in the tails on the left and the right, an extra 0.3%. And if I take that 0.3 and I divide it in half, I get an extra 0.15. Now my numbers add up to 100%. So anything above 3 or anything below 3, we just say is about 0.15% of the data. Okay. On the horizontal axis here, you can see how it's labeled too. X bar is right in the middle, and then it says plus 1s, plus 2s, plus 3 s's, minus 1s, minus 2s, minus 3 s's. So it's just plus 1 standard deviation, plus 2 standard deviations, plus 3 standard deviations, minus it's on the left. That's what all those labels are. Okay. All right. The other handout I gave you, we're going to do some questions off of there using this information now. And we're going to do the first one together. Okay. So I've got a standard bell curve here. This is what I mentioned. Sometimes it kind of looks like it's set to the axis. Just remember it's not. Set of data has a normal distribution, so we know it's going to be that shape even if they don't give us this picture, with a mean of 5.1 and a standard deviation of 0.9. We're going to sketch it, we're going to label our axes, and then we're going to find the percent of data that will fall within each of these ranges using our picture. All right, so first thing you need to remember is the mean is always in the middle. It's symmetric. All right, so there's my mean X bar, which in this example is 5.1. Okay. Then above each of these tick marks, those are representing plus 1, plus 2, and plus 3 standard deviations, minus 1, minus 2, minus 3 standard deviations. So I'm just going to say plus 1s, plus 2s, plus 3s, minus 1s, minus 2s, minus 3s. Sometimes they'll just label it like that. In this case, we can go a little further because we have actual numbers. If my mean is 5.1 and my standard deviation is 0.9, if I add 1 standard deviation on, I get 6.0. If I add another standard deviation on, I get 6.9. If I add another standard deviation on, I get 7.8. We're just adding that standard deviation value as we go to the right, and then as we go to the left, we take it away. Take away 0.9, I get 4.2. Take it away again, I get 3.3. Take it away again, I get 2.4. Okay, now those numbers are what we can use to answer these questions, and I'm going to kind of bounce around here a little bit. let's say I want to find the percent of data that is between 6 and 6.9. Okay, well, 6 and 6.9, it's that shaded region. And the picture that you just put on your purple packet can probably answer this for you. If I am between 1 and 2 standard deviations, what percent of the data is located there? It is 13.5%. Okay. I want to know what percent of the data is between 4.2 and 5.1. That's just one standard deviation to the left of the mean. What percent is located there? 34%. Okay, I'm going to jump around between 4.2 and 6.0. What is it, 60? 68. How do you get 68%? You can do 34 and 34, or you can use the empirical rule and know if I'm within one standard deviation, it's 68%. It's called the 68, 95, 99.7 rule for a reason. Okay. Then, let's say I want to know the percent of data that is less than 5.1. 50. That's easy, right? Because isn't 5.1 my mean? So I actually will often use that as a point of reference. If I'm at my mean, you can add up all those numbers if you want to, if you don't trust me, but it is always 50% to the left and 50% to the right. We've got a quick total there. Okay, I want to know the percent of data that is greater than 6.9. Greater than 6.9. So greater than 6.9 would be not including everything down here, just including everything up here. 2.5 is correct. There's two ways you can get it. You can say this is 2.35, and then anything past that is another 0.15. That's our 2.5. You could also say, okay, well, I know 50% of my data is here, so I'm excluding that. I know there's another 34 here, and there's another 13.5, so you can just take 100%, take away 50 and 34, 13.5, and also get that 95% we're taking away, leaving us with 2.5, okay? Less than 4.2. 16% is correct. So if I were going to do that, I would think, okay, well, I know 15 or 50% is to the left of my mean, and I want everything down here, so I'm just going to take out that 34% that I don't want. 50 minus the 34 is going to give me a 16 pretty quickly. So what if I wanted to know the percent of data that was greater than 4.2? It would be 100 take away 16, it would be 84. Or we could add things up. We could say this is 34 plus another 50. That's going to give me 84% also. Does that make sense? Okay. The two problems at the bottom, let's call this advanced level. You guys are going to try these. Find at least one friend, even a group, 3 or 4, work together, see what you can do, read very carefully, and then we're going to check our answers, and that's it for today. Okay? At that top one there. Let's see. 85 and 3.5 are the correct answers. If you had 7, it's because you didn't realize there were 2 standard deviations. If it tells you within 95% of the data, that's 2 standard deviations. So there's actually a standard deviation that's not drawn in there. So you divide that 7 in half. You get that 3.5. And I labeled more really than I needed to there. That's the main idea with that one. Okay, so if it said like 99.7%, I would know that's 3 standard deviations. And so I'd have to take what I have and divide it by 3. Okay, the bottom one, this is what your just sketch would look like if you wanted to label the mean in the middle and then plus and minus 3 standard deviations. Just keep adding and subtracting 10. You need to find the percentages like we did in the previous problems. But then the question wasn't asking what percent of the students, it was asking how many. So for the first one, we know 2.5% of 230, and we know of in math means multiply. So that's what we're doing. And then we can't have part of a student, so it just makes sense to naturally round to the nearest student in each of these. Okay, so I'll leave that up there. You can correct anything you need to. Are there any questions on the empirical rule? Yeah.
So like when we're finding people, you just round normally. So if it's below 0.5, you just round down.
Right. We'll have certain instances that will round up always or round down always, but for this, I think just
Because I thought like maybe you round up just to like
account for that extra percent. Yeah, I mean, Math Excel, when you do it, it'll be really specific, but I'm okay just rounding to the nearest value in general. Yeah. Okay, I'll do cell phone lotto. Remember, we're not quite done with 2-4. What's on the back of that paper is what we're going to finish up on Monday, and then everything that's on your calendar is pushed back a day for next week. Okay? Alright, go up there, you can grab it. Again, you can just continue to work on your 2, 3, 2, 4 Math Excel assignments as you wish.